All right, so now we're ready to finally predict the reaction type. We're going to be predicting between SN2, E2, SN1, and E1. So we've already done some predictions between SN2 and E2, so what we're essentially going to be doing now is adding in a third column to our table to predict SN1 or E1. So let's go ahead and make a little table here. And we'll start off with making of course, our listings. Good, fair, poor, and not applicable. And we've already looked at, didn't realize I'm zoomed in. We've already looked at SN2, and we know that SN2, the good, fair, poor rating is based on the sterics of the substrate. So good would be a primary substrate. Fair would be secondary. And tertiary is poor. And then finally, we talked about not applicable for SN2. That is if you have a poor or bulky nucleophile. Okay. And we saw examples of poor and bulky nucleophiles in the previous lectures. Just to recap, the poor nucleophiles are water, carboxylic acids, and alcohols, in addition to the mineral acids like HBr and HI. So none of those things are ever going to do SN2 in this class. And the bulky nucleophile is the tert-butoxide base, the OTBU with some counterion like sodium, lithium, potassium, cesium. So like potassium tert-butoxide would be a bulky nucleophile. It won't do SN2. E2, that had everything to do with the base strength, which was determined by the pKa of the conjugate acid of the nucleophile. So if the pKa of the conjugate acid was greater than or equal, actually, to 16, that was good. Between 0 and 16, not including 0 and 16, just in between that range, that's fair. And then less than or equal to 0, that's poor. And the E2 reaction could be Na if there's no beta hydrogen. Remember that E2 reaction requires a beta hydrogen attached to an sp3 hybridized carbon. So if you don't have that, you're not going to be able to do your E2. Okay, now here's the part you've all been waiting for, a new column. And actually SN1 and E1 are going to share this same column. And the reason is that E1, you can always tell when it's going to be E1. It's easy to tell E1 because you're looking for H2SO4, heat, or toxic acid and heat. So those are the two conditions that force E1. You're never going to see an E1 reaction without those conditions. So you don't really need the table for that. So really this column is for SN1. An SN1 column is actually the opposite of the SN2 column. So tertiary substrate is good. Secondary, fair, and primary is poor. Now, I wish it was just this simple because it's so beautiful, but I do need to make a modification here because if you remember, the SN1 reaction depends on the stability of a carbocation intermediate. And we saw that tertiary carbocations were not the most stable. There were some special carbocations that were more stable than even tertiary, and those were the allylic, the benzylic, and the heteroatom stabilized carbocations. So we need some way of addressing that in our table. So what I'm going to do is actually right underneath where it says good on the SN1 column, I'll put some parentheses here. And there's another way that SN1 E1 column can become good. If you have a primary or secondary allylic or benzylic substrate, that is, when the leaving group leaves, if it creates at that position an allylic or benzylic carbocation, that is what we would call an allylic or benzylic substrate. And this is good if you have a neutral, that means not a charged nucleophile. Okay? So if you have a primary or secondary allylic or benzylic substrate with a neutral nucleophile, that will be a good entry for our SN1E1 column. And we will look at examples of this. For the fair column, we also want to add primary or secondary allylic or benzylic with negatively charged nucleophiles. That is going to be upgraded to fair. That is going to be upgraded to fair. So really that's primary substrates, because secondary is already fair. So we're talking specifically about primary allylic and benzylic substrates with negatively charged nucleophiles. Those are going to get upgraded from poor, because primary would normally be poor. Those will get upgraded to fair. Okay, and then whether you have secondary or primary, if you have a neutral nucleophile with your allylic or benzylic substrate, that's going to upgrade to good. And there's no Na for the SN1E1, so there's no Na to worry about. Okay, so aside from the little allylic benzylic substrate part, it's a pretty straightforward column. So now let's go ahead and do a bunch of examples, and then we're going to have a great day. Okay, so let's do an example here. I've got a lot of examples for you. Okay, first example, we are going to take this alkyl halide and treat it with NaOAC. Let's predict which reaction will occur. So the first step is to identify the leaving group. We want to make sure we have a good leaving group, because if we don't have a good leaving group, there'll be no reaction. No SN2, no E2, no SN1, no E1. You need a good leaving group for all of these reactions, and it's the same 5 leaving groups for all of them. In this case, we have bromine, which is one of our good leaving groups, so we don't have to worry about that. Although it's kind of nice, if I don't give you a good leaving group, you just say no reaction and you're done. The nucleophile, the second thing we want to identify is the nucleophile. The nucleophile is negatively charged, OAC minus. The sodium is just a counterion for this ionic sodium acetate. So the nucleophile is actually the OAC. The sodium's not actually part of the nucleophile, it's just a spectator. The conjugate acid is HOAC, which is the carboxylic acid, which is pKa5. Remember, the structure of HOAC is acetic acid, which is a carboxylic acid, which is pKa5. So now we can do our table method. So SN2, E2, SN1, E1. SN2 is going to be fair because it's secondary. E2 is going to be fair because its pKa of the conjugate acid is 5, which is between 0 and 16. And the SN1, E1 column is going to be fair because it's secondary. So we have a 3-way tie, and we want to go with the first best option, meaning the most left option that's the best. In that case, SN2 wins the 3-way tie. Because we go with the first best option. So now we can just draw the product. Where we replace the leaving group with OAC, and because it's SN2, the stereochemistry flips from a wedge to a dash. Don't forget that. All right, let's do another example. Let's do a tricky one here. Here's an example where SN1 wins. I guess maybe I shouldn't give you spoilers, but it's okay. Maybe you would see that SN1 wins right off the bat. And okay, what's the product of this reaction? Okay, let's go through the steps. Number 1 step, first we need to identify the leaving group. Our leaving group is OTS. That's a good leaving group, so we're going to keep going. Remember, tosylate is one of our 5 good leaving groups. It's a sulfonate. Number 2, what's our nucleophile? It's HOAC, acetic acid. Conjugate acid of our nucleophile is H2OAC plus, which might have the following formula. Bond line structure looks like this. It's a protonated carboxylic acid. What's the pKa of the protonated carboxylic acid? Uh-oh. That's not on our pKa table. It's not a protonated alcohol. It's a protonated carboxylic acid. So not on pKa table. We're going to need to figure out the base strength, but that conjugate acid is not on the pKa table. So here's a little trick. You can estimate pKa by subtracting 20 when you form the conjugate acid. So roughly when you add a proton, and this is a rough approximation, the pKa goes down by about 20. Consider, for example, the pKa of an amine. An amine is pKa 38. And if you protonate it to become ammonium, we know from our pKa table that that is 10. So that's a difference of 18. So it's roughly a 20-fold difference. Okay, roughly a 20-fold difference. And you can look at the pKa table at a few other examples, like the alcohol versus the protonated alcohol. It's about a 20 difference. So we can estimate the pKa of this protonated carboxylic acid as being 5, which is the pKa of the carboxylic acid, minus a pKa penalty of 20 for being protonated, gives us negative 15 as our possible pKa value for our protonated carboxylic acid. In other words, this is a terrible base. And that makes sense, right? A carboxylic acid is not going to be a very strong base. So we would expect that the pK of the conjugate acid to be quite low. Okay, now we can do our table method. So SN2, E2, SN1, E1. Okay. SN2 is going to be not applicable. We have a poor nucleophile. Remember, carboxylic acid is one of our poor nucleophiles. Water, carboxylic acid, alcohol. So SN2 is Na. E2, poor, because the pK of the conjugate acid is negative 15, which is much less than 0. So that is going to be poor. And then SN1E1, it's tertiary, so it's good. So among Na, poor, and good, SN1E1 clearly is the winner. Now, we know it's not E1 because the conditions are not H2SO4 and heat. So we know it's got to be SN1. If it's anything but H2SO4 and heat or toxic acid and heat, then it's definitely not E1. It'll be SN1. So we can go ahead and draw the product. Start by redrawing the starting material. And so the product would be replacing the leaving group, OTS, with OAC. And remember, because this is a SN1 reaction, we get a racemization occurring so that the nucleophile will approach as a wedge and a dash. This is kind of a dumb example because this is actually not a stereocenter since there's two ethyl groups. But we can just pretend when you do an SN1 reaction, you get racemization, which means you get both stereoisomer products. When you do an SN2 reaction, you invert the stereochemistry. When you do an SN1 reaction, you randomize the stereochemistry, make it 50-50 at that position. There is no reaction that maintains the stereochemistry. You're either going to flip it or randomize it. There is no possible way to keep the stereochemistry the same. One possible way, if you want to do a reaction to keep the stereochemistry the same, is do two SN2 reactions in a row. That will flip it and then flip it back with the second SN2 reaction. So that's one way that you can keep the stereochemistry, but that's not what's happening here. Just to recap, let's take a look at the mechanism of what's going on in this reaction, just so that we can remember how the SN1 reaction works, since it is relatively new for us. Okay, the first step in the SN1 reaction is that the leaving group leaves in a process called dissociation or solvolysis. And when that occurs, we end up with a carbocation. And we lose all stereochemistry on that carbocation. The carbocation is sp2 hybridized. There can never be wedges or dashes coming out of sp2 hybridized carbons in this class moving forward. Now that we have the carbocation, the next step of the reaction is nucleophilic attack. The acetic acid is going to act as our nucleophile and attack the carbocation, leading to the nucleophilic attack product. That looks like this. Okay. And then finally, last stage is a acid-base reaction. You can either have the acetic acid, another molecule, come in and act as the base, or you can just draw a generic base, B with a lone pair, to grab that pesky proton, neutralizing the charge on the product and leading to our final answer, which is the SN1 product. Now note, instead of drawing both products, the wedge and the dash and the wedge, the 50-50 randomization, you can save time. No wedges or dashes. If you do that, if you don't draw any wedges or dashes, I will assume you mean racemic. And racemic, as a reminder, means 50% wedge and 50% dash. So unless I tell you to draw each stereoisomer explicitly, you can just draw no wedges or dashes at all, and I will assume you know that means 50-50 one and the other. So that is very commonly done for an SN1 reaction, that if the product is chiral, instead of taking the time to draw the molecule twice, they just don't draw wedges or dashes at that stereocenter. Okay, let's take a look at another example. Okay, what's the product of this reaction? What's our leaving group? I minus, one of our good leaving groups, so we're good. What's our nucleophile? It's OAC minus. It's a good nucleophile for SN2. The conjugate acid is acetic acid with pKa of 5. So now we can do our table method. SN2, E2, SN1, E1. Okay, the SN2 column is secondary, so fair. The E2 column is secondary. I'm sorry, not secondary. It's fair because the pKa is 5, so 5, fair. Remember, E2 depends on the pKa of the conjugate acid. In this case, it's 5. And then the SN1 E1 column is secondary, but benzylic. Remember, if you have a leaving group that's on the carbon next to a benzene ring, that's considered benzylic. And if it's a carbon next to a double bond, just a double bond, that would be considered allylic. And this is benzylic with, is it a neutral or negative nucleophile? This is a negative nucleophile because it's sodium plus OAC minus. The nucleophile has a negative charge. So this is benzylic with anionic or negative nucleophile. And if you recall, if you have something that's secondary but benzylic with an anionic nucleophile, that gets upgraded from fair to fair. So it's still fair. Secondary is fair, but benzylic with anionic nucleophile is also fair. So for two reasons, this is fair. And just to show you the resonance stabilization that can occur here, look what happens in an SN1 reaction. The leaving group leaves in the first step, it's the dissociation step, to leave behind a carbocation right where the leaving group was. And now that carbocation is benzylic. It's resonance stabilized. You can start drawing a bunch of resonance structures. I won't go ahead and draw them all, but ... You can draw a bunch of resonance structures all around the ring showing the stabilization of that carbocation. All right, well, anyway, we have a three-way tie, fair, 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 and we know who wins three-way ties. It's SN2, so all of that conversation was a waste of time anyway, because SN2 is going to win. So we can go ahead and, why don't we draw the mechanism and the product? Mechanism. I like this. I think this is like a puzzle. This is the kind of thing that attracts me to chemistry, is because this is like a puzzle. It's like a game, and I never knew that this is a game that people can play. It's kind of fun. Maybe one day they'll put these kind of things in newspapers where the crossword puzzles are. Okay, there's the mechanism of the SN2 reaction. Remember, it's all a single step. The nucleophile does backside attack, displacing the leaving group and replacing the leaving group with that nucleophile, making sure to change that dash, to change that wedge to a dash. So plain old SN2. Okay, let's try another example. Okay, let's do the exact same substrate actually, because this has got interesting considerations. And we're going to change our nucleophile now to the thiol. number 1. I minus, good leaving group. Number 2, nucleophile is the thiol. Conjugate acid of the thiol is the protonated thiol, which has pKa of -7. So now we can do the SN2, E2, SN1, E1. Okay, SN2 is secondary, so fair. E2 is -7, which is poor. Conjugate acid is -7, definitely poor. And then SN1E1, it's secondary, but benzylic. With neutral nucleophile. The thiol is not anionic. There's no ionic bond there making it negatively charged. It's neutral sulfur. No charge here. Neutral sulfur. So that actually gets upgraded to good for the SN1E1 column. Remember, benzylic or allylic with a neutral nucleophile is always good. So ding, 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 we have fair. We have poor, but we also have good. SN1 wins, the unlikely winner. A lot of times it's hard for SN1 to win because it never wins ties. SN1 loses ties to SN2 and E2. So we always get a nice cheer, a nice hurrah when SN1E1 column can win. The product of the reaction? Well, it's going to be the substitution product. Of course, it's going to be racemic. So we're going to have both stereoisomers present. Let's take a look at the mechanism. How does this reaction occur? Remember, the first step of the SN1 reaction is dissociation of the leaving group to give us a resonance stabilized carbocation. Well, not always resonance stabilized, but in this case it's a benzylic, quite a stable carbocation. Next step, the nucleophile attacks. In this case we have ethane thiol acting as a nucleophile, attacks that carbocation. And it's going to create a new sulfur carbon bond. Of course, there's not going to be any stereochemistry there. It's going to be 50-50 chance from the top, 50-50 chance from the bottom. So instead of drawing a wedge or a dash, I'll just leave it as a straight line to show that it's racemic. And there's a product after nucleophilic attack. That sulfur's got a positive charge because it's got a pesky proton on it. We can fix that with a final step of the SN1 reaction, which is an acid-base reaction. The base is going to come along. I'll just draw a generic base. Take that pesky proton away and lead us to our final product, which is the racemic SN1 product. That looks like that. You may see another convention that's sometimes drawn. It's a squiggly line. So if you see the squiggly line, that also means racemic. Unfortunately, the squiggly line can also mean that the stereochemistry is unknown. So I don't know, some chemists think it means racemic. Some chemists also think that it means the stereochemistry is unknown or undetermined. But in this class, if you see the squiggly line, it means racemic. All right, let's just take a look at one more example, and you'll have lots of practice to do with these on your problem set. Let's do this one here, final example. Okay, there's NaCN and methanol as a solvent. Okay, let's figure out the reaction. So SN2, E2, SN1, E1. I haven't even bothered to do an E1 reaction because E1 is so obvious, it's so easy. You just look for H2SO4 in heat or toxic acid in heat, and that is automatically E1. SN2 in this reaction is going to be tertiary, so poor. Oh, we didn't do our leaving group analysis. Our leaving group is Br minus, and our nucleophile is Cn minus with the conjugate acid of HCN, which has a pKa of 9. So that's going to be pKa equals 9, which is fair. And then finally the SN1E1 column, it's tertiary, so that's good. So look at that. We have poor, fair, good. SN1E1 wins again. Love it. Well, technically SN1 wins. E1 doesn't win unless it's that special condition. So it's going to be SN1 reaction. So let's go ahead and take a look at the mechanism. Okay. First step of an SN1 reaction is always the same. It's always dissociation of that leaving group. The leaving group is just going to get up and say, I'm out of here. And so that's exactly what it does. The bromine just leaves. When that happens, we lose the stereochemistry at that position because it's sp hybridized. Now, our nucleophile can come in. Cn minus. Remember, methanol is just the solvent. Cn minus is our nucleophile that attacks that carbocation. And now we're left with the racemic product. So we have Cn going up, and we also have the product where Cn's going back, as is the case with these SN1 reactions. And notice that we have no need for an acid-base step because you never need to do acid-base with an anionic nucleophile. NaCN is an anionic nucleophile. If it happens to do SN1, which is rare, typically the anionic nucleophiles will be able to do SN2, but if somehow it ends up getting all the way to SN1, you can skip the acid-base step because you'll notice there's no proton to even remove from the nucleophile, so no need for acid-base step. We're already done. Product already neutral. Smiley face. Okay. All right, so that's enough examples for today. You'll have more opportunities to do that, practice on the problem sets. I just want to show you, it's really more of a confession that I lied to you, and I think I told you that I lied to you. I want to do an old reaction revisited. Now that we know the SN1 reaction, I need to come clean here. And I'm going to put old in parentheses here because I think you know what I'm referring to. Of course, I'm referring to the old school method. Remember the old school method? That's okay, I'll refresh your memory. The old school method is when I told you it only worked with primary alcohols. That was my lie. And you treated it with something like HCl, HBr, HI. And the mechanism was that the alcohol became protonated by that mineral acid to form the protonated alcohol. And then the conjugate base of that mineral acid, in this case Br minus, would come in and act like a nucleophile in an SN2 reaction, kicking out water, which is one of our good leaving groups. And so this was a way that we could get alcohols to participate in SN2 when normally they wouldn't because OH is not a good leaving group. But in reality, OH is still not a good leaving group. It's just that the HBr converts the OH into a good leaving group, water, and then does SN2. So that the product, the net result, is replacing the OH group with the halogen group. So now, here's where I lied. I said it only works for primary alcohols, but actually it does work with secondary and tertiary alcohols. It just goes through a different mechanism. If a primary or secondary alcohol is used, SN1 mechanism occurs. So let's see what would happen with a, I'm sorry, not a primary or secondary, tertiary or secondary. We know what happens if it's primary, does SN2. If it's tertiary or secondary, does SN1. So let's take a tertiary alcohol, terbutanol. And we're going to treat that with, say, HCl. And the first step is going to be the same. The OH group is going to get protonated by the HCl, kicking out chlorine. And we'll get the protonated alcohol just like before. Now the difference is the chlorine is not going to do SN2 on that good leaving group. Instead, we're going to have a dissociation step occur. So the water is just going to leave now to give a carbocation. And then chlorine's going to come and do nucleophilic attack on the carbocation. So that's SN1. And that's going to give us the product. And this works with HCl, HBr, and HI. Doesn't work with HF. So coming clean, I lied to you. I just didn't know how to explain it to you at the time. Now I feel like we can talk openly and freely, and I can be comfortable around you guys now that you know the SN1 reaction. And I can be honest and say that the old school method works on tertiary and secondary alcohols via an SN1 mechanism. I should also mention that secondary and tertiary alcohols can be forced to do E1. So secondary and tertiary alcohols can do E1, since if you remember, the E1 conditions are also strongly acidic. Sulfuric acid and all that good stuff, tosic acid, in the presence of an alcohol is going to protonate it and make it a good leaving group. So let's take a look at an example. So if I took this alcohol and treated it with H2SO4 and heat, I'll actually draw out the structure of the sulfuric acid. Remember, here's the structure of sulfuric acid. The alcohol in the first step is, and heat, don't forget heat. Gotta include that heat. The lone pair on the alcohol will attack the proton of sulfuric acid to give us a protonated alcohol. And this is a secondary alcohol, so it is going to dissociate to give the carbocation. And then there's going to be an acid-base beta deprotonation as part of the E1 reaction. A generic base is going to come along, remove the beta hydrogen, and that's going to give us the alkene. So E1 reactions work on alcohols, even though OH is not a good leaving group. And the reason they work is because the E1 conditions, by coincidence, happen to be highly acidic. When you put an alcohol in a highly acidic environment, it protonates the alcohol, turning it into a good leaving group, and then reactions like E1 and SN1 can occur. And this reaction has a special name. It's called the dehydration of alcohols. Because if you look at what's actually happening, the water is getting removed from the alcohol. So it's being dehydrated. And when you remove water from something, you're going to call that dehydration. I don't know. I'm going in circles here. That's the name of this reaction. We don't call this the old school method E1. We just call it the dehydration of alcohols. And this does, and I'm not lying to you, it only works with secondary and tertiary alcohols. Primary alcohols, they do something different if you treat them with E1 conditions. We'll get there. We'll talk about what happens if, just remember that I'm not telling you right now, but primary alcohols do something different with these conditions, and you'll find out soon enough. Okay, well that's it for now. We're going to move on to a new topic, and we're going to talk a lot about alcohols starting next time. So, all right, see you then.